So this is going to be some exam feedback for the practical geochemistry and data analysis exam. So it's just going to be questions 2 and 4, which were the stable isotope questions, which I was responsible for. But before we move on to the questions in detail, just some generic advice on kind of exams. So first of all, really read the question and figure out specifically what the question is asking of you. Maybe just make some notes in your exam book about what you're going to write, and really check that what you're going to write about is what's being asked of you. So it's quite common for students to lose a whole bunch of marks in exams because they write down a whole bunch of stuff which is really factually correct and accurate, which is great, but doesn't answer the question. Okay, so it's quite common for students to kind of answer a question which is from a previous year's exam, or one which is just writing lots and lots of things that they know about a subject, which is good in some ways and shows that you've at least learned something, but doesn't answer the question being asked of you, therefore you don't get very many marks. Sometimes none, which is a real shame. So do read the question, and as a kind of a revision tip for I guess making sure that you understand exam questions and what we're asking of you, is it's maybe a good idea to rewrite exam questions in your own words, and then discuss them amongst your friends in group revision, post them on the discussion forum so I can maybe comment on them, or just ask me at the end of a lecture or in office hours or something like that, and just to check whether you've got the meaning of the question correct. So it's a good way of making sure that you've comprehended the sets of questions. Okay. Another thing that you could maybe think about doing is going through kind of your lecture notes and trying to write your own exam question. Okay, and then bringing that to the end of a lecture, or bringing that to this discussion forum, and seeing if you've identified the important parts of the content that's in the course. Another thing that's particularly important when you've got questions in exams where you're being asked to calculate an answer for something, a numerical value of a thing. In this exam, I asked you to work out the temperature of the deep ocean in the past, and it's really important that you think about your answer once you've worked it out. So there are quite a lot of people that did a calculation, came up with an answer, and then moved on to the next part of the question, and it was clear that they'd not really thought about, or there was no evidence that they'd thought about, so there's not written down anything in the exam book about, is that a sensible thing? Okay, so in this example here, we've got some temperatures. Okay, so we think about what are temperatures. These are approximations to some of the answers that were given. So for instance, if you give an answer for the deep ocean of 1,000 degrees Celsius, I mean that's obviously not feasible. No part of the ocean is that hot as a liquid anyway. And even an answer of maybe 20 degrees Celsius is probably a little bit warm for the temperature of the deep ocean. If it was surface water, maybe some surface waters can get up to 20 degrees C. That might be feasible. Likewise, an answer of -10. Okay, so it's far too cold for water to be liquid at that temperature. So unless the whole ocean has frozen in the past, then we can't have a temperature of -10 degrees Celsius. And even if that was the case, and it's not, then no foram could grow in ice. So, or at least not complete ice anyway. And then there were also some people that had temperatures of negative kelvins, which is physically impossible. So that's a thing that you should have. If you come up with that answer, even if you're not going to recalculate it, or you can't figure out where you've gone wrong, write a little note in your exam book. This is obviously wrong, and this is the reason why. And there's a chance that you would get some credit for at least figuring out that is the wrong answer. So some people did that for the answer, which was actually quite close to a -1 degree C, and they said, "Oh, that can't be right." Because the water would be frozen, which is not completely unreasonable thing to say, but in the case of this question, it was to do with the ocean, and the ocean is salt water, and salt water doesn't freeze at -1 degree Celsius. So so therefore it's an allowable answer. Okay, but putting that kind of, I guess, bit of critical analysis of your answer is important. Moving on to the kind of things that are now being expected of you at honours level rather than at pre-honours level. So we're rather than kind of I guess churning out material that's been given in the lectures and kind of writing that down again, we're really asking you to apply some of the things that you've learnt in the lectures and in practicals and in the reading, and apply that knowledge and kind of those concepts that you've learnt to new problems. So we're really asking you to think a little bit more in exams. Okay, and one of these areas that we're asking you to think is in critical analysis. And what, one aspect of critical analysis which is important is kind of when you come up with an answer, what are the assumptions to that? What are the potential weaknesses to that answer? What are the strengths to that answer? Write those things down. And in some of the questions asked, I explicitly even say what are the assumptions. But rather than just listing the assumptions, you can also take it to the next level and to say, well, are these assumptions good? How much of the answer depends on this assumption, or is this assumption only a kind of a minor kind of detail causing a small amount of uncertainty in the answer? Okay, or is this assumption kind of hugely important? Does it blow up the answer completely? And this is would be a bad assumption to make. Okay, right. So moving on to the questions now. So the first question I asked, that came up in the exam, question 2, about stable isotopes and paleothermometry. So I give you a bunch of information here. So I give you this equation that is an empirical calibration between the fractionation factor between calcite and water and the temperature at which that calcite precipitated from that water. And then some information. So there's some benthic foraminifera. So these are things that live on the bottom of the sea in the sediment, and they've got an oxygen isotope value, a ratio expressed in this delta notation of plus 1.04, and those were sampled from water, or the core was sitting in water, so there's an assumption that those forams grew in that water at 5 degrees Celsius. And then further down the core we've got some other foraminifera which are older. They're 150,000 years older, and they have got a slightly more positive delta 18O of plus 2.32. Okay, so the first question that's being asked is to calculate the temperature of the water in which those older foraminifera grew. Okay, so important things in here. We also explicitly ask you to state your assumptions and to show your workings. Okay, so show your workings is always a good idea, but put that in there just to remind you. So this is the information we're going to start out with. Okay, because what we need, okay, is the calcite and the water at the time of the temperature we're interested in. Okay, so this is at the time 150,000 years ago. So we don't have all of that information yet. So we have the benthic oxygen isotopes of forams that have been kind of grown now, and we have the water temperature now. So one of the things we can do with that information is work out what the isotopic composition of that water is now, and then we can then use that. So we can then use that to then work out what the temperature was in the past, using the past calcium carbonate oxygen isotopes. So before we go into that, the key piece of information that was missing in quite a lot of answers, which basically stopped you being able to work out the correct answer, was this relationship here on the right. So this is an approximation that the fractionation factor, well, the natural log of the fractionation factor times 1,000 can be approximated to the difference in the delta values and the per mil oxygen isotopes between the two phases. So in this, if you didn't know this, you were not able to answer the question properly. And you should know this because we did go through this extensively in one of the practicals. So you can basically replace this here with this here, and this makes the equations a lot easier to work with. Okay. So what, and the other piece of information that you needed to do, you needed to convert your temperatures into Kelvin. So that's a thing you should have known. So the approach here is we're gonna calculate the delta, the oxygen isotope delta 18O of water now, and then we're going to make some assumptions, and the assumptions are the water composition was the same now and in the past, and then we're going to make another assumption, which I also already mentioned, that the core top samples of 0 age are actually 0 age and represent precipitation from modern water. And then we're going to use that kind of this water composition with the calcite composition of the older samples, okay, to work out the paleotemperature. So I'm just going to go through that in some detail now. So this is the equation that we've basically now got. So this is for the modern ocean. So we've got this modern temperature, 5 degrees C here, okay, and I'm going to substitute in for calcite, okay, the value of modern calcite, okay, and then I can rearrange this equation to get an equation for the isotopic composition of water now, and that's this thing here. So you could, if you wanted to, work out what that number was and then use that number, but you don't have to. You could just keep that equation and then manipulate that equation as it goes, and then stuff might cancel out, which we'll see it will. So we're then going to take this value for water, okay, and then plug that into our equation for temperature. So we're going to put this whole thing in here, and we're going to put the composition of the isotopic composition of the calcium carbonate into here, and that will enable us to calculate the temperature at that time. Okay, so that's what I've done here. So this is basically just substituted in this equation down here, and the carbonate composition there. Now we can just get rid of that bracket. So important thing to notice here is this minus sign here, so that means that all of the things inside the bracket change sign. So this means that now we can start to think about cancelling some stuff out. Minus 32.42 on both sides, so they magically disappear. And now we then have one equation which has got a whole bunch of numbers in it and one unknown. Okay, so this is great, which means that we can work out that unknown, and we can do that just by rearranging that equation. Fairly straightforward, which gives us that. And then we just, plug and chug and get our answer, which is it's 272.77 Kelvin, or minus 0.39 degrees Celsius. Okay, so at this point you might want to think about, is that an appropriate number, okay, to give us an answer? Also, is it an appropriate degree of precision? Okay, is it appropriate to quote that to 2 significant figures, as I've done there, or is that a bit too precise? What is the precision of the information that I've been given? Which brings us on to the next part of the well, that will come up in part B, I think. Anyway, so now we do need to think about, have we actually mentioned all of the assumptions, okay, which you need in this to get all of the marks. So we've also mentioned some of them. So was the water the same now and in the past? And you could add a little bit of critical analysis in here and say, well, this is 150,000 years ago, marine isotope stage 6, so this is maybe a glacial period. Doesn't really matter if you knew that or not, but over such a long time period you might have changed the amount of ice on land, and the oxygen isotope composition of the whole ocean may have changed over that time. So that's an assumption that we've made, and you could maybe have some critical analysis here saying, is that a good assumption or not? Already mentioned that we're assuming that the samples at the top of the core are representative of carbonates that are precipitating from the modern ocean, so that's usually a good assumption. We don't have any information to say whether that's a good or bad assumption here. an assumption that's quite often made with stable isotope paleothermometry is stuff precipitates in isotopic equilibrium. In this case, we don't actually make that assumption because we're using an empirical calibration. But you could say, you know, something about either the assumption of equilibrium or the assumption that the calibration that's been maybe made on modern samples is valid back in time, maybe with slightly different forams. We could make an assumption about are the forams the same species or not, but again, that's information that we don't have or isn't given in the question. And then the classic catch-all, which is always worth mentioning when you're dealing with any kind of paleoceanography, is that has diagenesis affected our samples? Okay, and there's no information in the question about whether this has happened or not, but it's something that kind of needs mentioning with most geochemistry or on kind of paleoceanographic kind of contexts. Okay, so I mentioned a little bit about precision, so we need to think about, you know, what is the ultimate precision of our answer, and one thing that, you know, we can think about is that, so I've written an answer down here, 272.77 Kelvin. Is that an appropriate degree of precision? So some of the information we were given was actually only given to one significant figure. Okay, so the initial temperature was only given 5 degrees Celsius. So it would be inappropriate for us to quote our answer to a higher degree of precision. So that's also worth thinking about in your answer. Are you quoting to the right number of significant figures? So another thing that you should have picked up on is that in the question that I actually did give you some uncertainties on some of the information given. So you could have gone through and seen how much that makes a difference. Okay, so if we've got an uncertainty in our mean value of the marine isotope stage 6 forams of 0.25, if we changed our measurement by that amount, you know, still within the measurement uncertainty here, then how much does our answer change? Okay, so we could do that. That's what I've just done here. I've just changed this value to, you know, 0.25 less, and we come up with a value here that is 1 degree Celsius different. So we could maybe say, commenting on the precision, that in this case we only really know our answer to plus or minus 1 degree Celsius. If we include the uncertainty from the other measurement, then maybe even higher uncertainty, maybe something like, you know, 1.5 degrees Celsius. So that would be worth, you know, that would have been required to comment on the precision. And then separately, you see it says precision and accuracy in the question, we could then go about and think about some of these assumptions in terms of the critical analysis. How good is this assumption that the water composition is the same in the past? You know, is it possible that the ocean oxygen isotope composition has changed through time? It has. So this is going to affect the accuracy of our results. Okay, and then similar things for some of the other samples, so some of the other assumptions. Okay, and then the next part of the question really asks, where's my little pointer, what might we do to improve these? Okay, so improve the precision. We can measure more samples. Okay, we could measure larger samples. That will reduce the uncertainty of the measurement of the mean. Okay, because the more samples you measure, the smaller the uncertainty on a mean gets. We could think about improving the accuracy of our results by maybe measuring other proxies for ice volume or other proxies for temperature to try and kind of maybe resolve some of these effects of seawater composition changing through time. Okay, so measuring multiple proxies is a good way of improving accuracies of paleoceanographic measurements. Okay, so the last part of this explain the mechanisms that cause stable isotope fractionations and the reasons that allow stable isotopes to be used as paleothermometers. So this question was really focused around, you know, why are stable isotopes useful for paleo temperatures. So quite a lot of people wrote a lot about isotope fractionation, but missed out on this, why they can be used for paleo temperatures. So this is really where it comes down to kind of really focusing on reading the question that's important. So to look at this question kind of quite broadly, kind of these are the key things that you kind of like really needed to bring to your answer here. So so in terms of the mechanisms that cause stable isotope fractionations, okay, so there are kinetic and equilibrium isotope fractionations, okay, and they arise through these kind of effects through bond strength and reaction rates. Okay, so for kinetic isotope fractionation, we're looking at, you know, your answer potentially including things like the equation that shows that the activation energy is important for reaction rate, and the activation energy is, you could then take it a step back and then go into some of the details about why heavier isotopes form bonds with higher activation energies, and then go on to say, well, if you have a reaction that doesn't go to completion, is one unidirectional, then the reaction rate will cause the lighter isotopes to be more enriched in the products of that reaction. Also, you could have gone in and explained the diffusion mechanism of kinetic isotope fractionation. This is where, you know, the lighter isotopes can diffuse faster because at the same kinetic energy they have a higher velocity. So that would have been required for the kinetic isotope fractionation. Kind of looking at the equilibrium case. Okay, so this is where we start to merge the answer for the paleo temperature part of the question. So for any kind of isotope exchange reaction, there will be a preference for the heavier isotopes to be concentrated in the stronger bonds. And again, you could have gone into some detail about why that is, but that would have, you know, that would have been to get to the higher and higher levels of more marks. But the key thing is that preference, okay, is driven by thermodynamics in terms of there is, if the fractionation factor is not 1, i.e. there is some preference of heavier isotopes in one of the phases, then that means that there must be something that's driving that that fractionation, some kind of delta G, and that delta G will be due to some isotope fractionation, which is the dependence or the preference for the heavier isotopes to go into the stronger bonds, and also some entropy. So the entropy is basically working against that. That wants it to be, everything to be mixed out. Okay, and this interplay of things wanting to be mixed at higher temperatures and things that want to be kind of separated into different phases due to their preference of being in different bonds leads to these relationships between temperature and the fractionation factor. Okay, so those equations, particularly this one and this one, where we might replace the log k here with a log alpha, those would have been good ones to have in your answer. Okay, and because we're now looking at an honours level thing exam, it would have been good to bring in some examples maybe in this case, and maybe talk about the example that's actually been used in the question, which is using calcium carbonate, and how the phases that are thought to be in equilibrium with each other are calcium carbonate and the water, or maybe some other examples where the phases are kind of indirectly in equilibrium. So the precipitation of minerals in igneous systems or hydrothermal systems at higher temperatures. So bringing some examples into your answer would have also been an appropriate thing to do. Okay, so moving on now to the question 4, which was about the use of boron isotopes as a pH proxy. So again, we're going to go through each kind of part of the question one by one. So the first part of the question was basically, in the above equation, what do alpha, epsilon and delta 11b mean? Okay, and the key things in this question here are this word mean. Okay, so we're going to define them, okay, and explain what they mean. Okay, and that's where I think quite a lot of people missed out on a bunch of marks because they either they didn't explain the meaning of them. So simply, alpha is the fractionation factor. So that's the ratio of isotope ratios between two phases in terms of the absolute isotope ratio. So this is the number of boron 11 atoms divided by the number of boron 10 atoms in a phase, in this case boric acid, relative to that in borate iron. Also, the question says in the above equations, so it's actually asking you to refer to the species in the above equations. So I didn't actually penalise people that much for not doing that, but it's a thing that's been asked of you, so you should have really been doing that. Epsilon, okay. In this case, epsilon is the fractionation is the fractionation factor expressed in terms of the per mil difference between two phases, assuming that one of the phases has got a delta value of 0. So I'll just bring in those explanations. So the fractionation factor is the absolute ratio of the two isotopes. The fractionation epsilon is the fractionation factor just expressed in a slightly different way. Okay, so this will be a number close to 1. Okay, 1.00 something. This will usually be a number that's between -10 and 10. So it's very similar to the delta 11b in terms of its appearance in number form, but it's relating to the fractionation factor between the two phases. So a bunch of people wrote down an alternative definition for epsilon, which was related to the delta value. So I'll just go through and explain the delta value first. So that's basically the parts per thousand difference in isotope ratios between a sample and an arbitrary standard. Okay, so that we use this to basically define the measurements that we make of samples in isotope geochemistry. And there is a use of this epsilon term in an equation like this, where the isotope variations are very small. Sometimes we use epsilon here and 10 to the 4 here. Okay, so the thing is that that's not what it's the case in this example. Okay, because in the above equation, that's not what it meant. Okay, it meant this kind of expression of the fractionation factor. Okay, so that tripped up a few people. Okay, so the next part of the question is really where most of the marks were. So this was a 50% of the marks for this question. Okay, so once again we had to refer to the above equations, use relevant diagrams. So this is giving you instructions about what really should be in your answer. We wanted you to explain why boron isotopes, okay, can be used to measure pH. So why is boron a pH proxy? Okay, so just to go through some of the slides from the lecture, which kind of explained why this is the case. So first of all, okay, the boron has these two species, boric acid and the borate iron. So this one and this one, and there's an isotope fractionation between those two, and that's due to because they have different bonding environments. You didn't need to know what it was. You didn't need to know exactly that it was 1.027, but you just needed to know that there was a fractionation factor between the two. And the other key piece of information is that the proportions of these two species changes with ocean pH, and that's because of this reaction here. So if we take boric acid, we add water to it, it forms borate iron and hydrogen positive ions, which means that the proportions of this species and this species can change depending on how many hydrogen ions there are around. So the more hydrogen ions we have, the lower the pH, the more it's going to force the reaction or the equilibrium over to this side to favour more boric acid. So you can see, so this was one of the diagrams which would have been useful to have. So at low pH, so pH 7, we've got mostly boric acid and a small amount of borate iron. Where at high pH, okay, the lack of hydrogen ions here drives the reaction over this way to produce hydrogen ions, and we have more borate iron than boric acid. Okay, so the speciation of these two phases is pH dependent. Okay, so the other thing then to note is that because there is an isotope fractionation between the two phases and the proportions of those changes with pH. That means that the isotope ratio of each of those species changes with pH. So with pH changing, there's a fractionation between boric acid and the borate ion, and that difference stays roughly similar across this range. But as we change from one species to the other, the isotopic compositions of those have to change to maintain the overall kind of isotope mass balance. So that means that the isotopic composition of borate ion changes with pH, which is important because carbonates only take their boron, they incorporate a small amount of boron into the calcium carbonate, they only take it from the borate ion pool. Okay, so that means that as pH changes, carbonates will be taking in boron of a different isotopic composition. Okay. So moving on to the next part of the question, which is what are the assumptions that go into this, and what are some of the weaknesses. So we've basically got this kind of this chain that we've this is the thing that we're measuring. Okay, the boron isotope composition of calcium carbonate, and this is the thing that we want to know. Okay, so the key assumption is that we go through. We need to basically go back through all of these steps to get to pH. Okay, so the first assumption that we're making is that all of the boron comes from this borate ion pool and not the boric acid. Okay, so that's an assumption we've made, and that's seemingly a fairly good assumption. And then we have to think about actually, is the boron isotopes in the calcium carbonate reflecting actually the boron isotopes that are actually dissolved in the water. Okay, and there will be some fractionation between those two because these are bound in slightly different places, slightly different ways. So there should be an isotope fractionation between those two, and it's quite hard for us to pin that down. So what we do is we do an empirical calibration. Okay, so we measure the boron isotopes in calcium carbonate on this axis, and we have some boron isotopes in the water, in the borate ion, in lab experiments, and we basically, this is what the theoretical value should be, and we have some empirical calibrations that depend on the species of the foram that's growing or the type of carbonate that's being precipitated. But it does mean that we can use those empirical calibrations to go back this step here. Okay, so we don't have to assume equilibrium between these two phases, between the borate ion and the carbonate, to get back to here. Okay, but then we also need to think about actually how do we go from the borate ion composition, the boron isotope composition of the borate ion, to pH. So the next kind of step is to think about all of the things that can affect that. Okay, so one of the things is we could change the whole boron isotope composition of the ocean. Okay, through bringing in boron from different kind of fluxes into the ocean, changes in weathering perhaps, but boron is quite a conservative element, so it's very hard to change the isotopic composition of the ocean, so that was a good assumption that we could make. The other things that we need to think about are some of the things that are going to affect that fractionation between, excuse me, the borate ion and the total boron pool. So that is actually going to be dependent on temperature as well as pH. Dependent on pressure, dependent on the sea level, so we're going to have some other proxies for that potentially. So a proxy for temperature might be magnesium-calcium ratio. If we measure planktic forams, we can assume that the pressure is going to be the same. And salinity is quite small, so we might be able to ignore that, or we could use potentially oxygen isotopes and magnesium-calcium to get the salinity of the formation of those forams. Another thing that we can do is check our answers. Okay, so in this case, obviously I've not asked you to calculate anything, but you can describe the process of going through and checking answers in terms of looking at how your measurements work in places where you actually know the answer. So in this case, a study where they've actually tried to reconstruct ice core based carbon dioxide based on the pH in the ocean. and seeing if they get the right answer. So that's another thing in terms of, it's always good to try and check your answers. So that's a thing that you could have mentioned in your answer as well. Okay, so just come over. So hopefully that explains kind of what I was looking for in some of the exam questions, and might help you in kind of future exams in terms of the tactics for revision and kind of what you're going to try and do to improve your geochemistry knowledge. Yeah. So also, if you're using this to revise for next year's exam or the year after, then hopefully you'll know what you're getting yourself in for. Well, not getting yourself in for, but we'll be able to use this as a useful tool to help you answer those kind of questions. Anyway, and that's the end of this.